Okay, we are going to go through the June 2024 paper 2, the even questions. Don't forget you've got your formula sheet, which is always useful to you. We will refer back to this later. Looking at this first question, we're told some researchers investigated the handspan in centimetres of adult pianists by their level, international, national and amateur. The box plots below give information about the handspan for our national level and our amateur level. Circle the word in the list below that describes handspan in centimetres as a type of data. So let's go through these. We've got qualitative, so qualities, well it's not quality. Ordinal, it's in order. Continuous, you can measure it on a ruler, on a stopwatch, something like that. Or bivariate, bi meaning two. So we're going to have continuous because we can measure it on a ruler. Next, the table gives information about the handspans of international level pianists. And we're told the greatest handspan, the median, lower quartile, range and interquartile range. So I always think it's useful to think about the key points that we need for a box plot because that's what we're asked to do in part 3. So I need the highest. Well, we're told that the greatest handspan is 27.4. We are told the median is 23.9. We're told the lower quartile is 23.2. But we're not told the lowest or the upper quartile. We're told the range, i.e. the difference between my highest and my lowest, and that is 5.1. So if I do 27.4, take away 5.1, I'm going to get 27.4, not 27.4, apologies. I'm going to get 22.3 for my lowest value. And then my upper quartile, we're told the interquartile range is 1.1, which means that my upper quartile is going to be at 24.3. Okay, lovely. We're then going to plot this onto our box plot. So taking my lowest value of 22.3. Now I think with a graph like this, it's really important to note what one little square is worth. 5 little squares is worth 1, so each little square is worth 0.2. So half a square is 0.1. So we're looking at 22.3. So find 22, then we're going 0.2 and then a half of the way along, like so. We're then going in for our lower quartile at 23.2. So finding 23 and then one box up. For our median, 23.9 now, so 23 and then half a box less than. Okay, my lines are a little bit wonky, or not wonky, but different lengths, not a problem. We've then got our upper quartile at 24.3, 24.2.3, and then I've got my higher at 27.4.2.4. And we then, in the classic style of a box plot, we can tidy that up. Okay, and this is where, if I had been sensible enough to draw this in pencil, I could tidy this up. Lovely. Moving on. Compare the 3 distributions of handspan. Give 3 comparisons and interpret 2 of your comparisons. So there are 3 things that we need to compare here. Okay, we need to consider our median. Okay, because that is going to tell us about, on average, in this case, how big are these pianists' hands. We need to discuss range. We need to discuss spread. So we're also going to consider interquartile range. And I always write myself these prompts to remind myself. And we then also, in that kind of addition for GCSE statistics versus just GCSE maths, we also need to consider skew. So we can look at these distributions. So when I think about my median here, and the nice thing about box plots is that we can really clearly see the differences. So I can see really clearly that for the median, or the international is bigger, then comes national, and then comes amateur. And I always like to compare those. So we could say that international is greater than national is greater than amateur. Like so. Okay. We're making that, okay? You could write that, or we could say that international pianists have the greatest median handspan. And then we need to interpret that. So what does that mean? That means that now what's really important is that we state the word median in there. Okay, so on average, international pianists have larger handspans. And that's our interpretation. And we can then do the same for our interquartile range. So when I look at my interquartile range, that's me considering kind of how wide my box is. So here I can again see, okay, this is the biggest, this is the smaller, this is the middle, and then this is the smallest here. So we could do the same thing. We could say international is smaller than national, which is smaller than amateur. And remember, what's that telling me about? That's telling me about spread. That's telling me about how much variation there is. So I could say that international pianists have the smallest interquartile range. Okay, this is now our interpretation. Handspan are more consistent. Okay, and we always talk about kind of more consistent when we look for that small interquartile range. Now thinking about skew, okay, so thinking about kind of which way is the distribution kind of loaded. We can see we've got a really high concentration here, and we've got 25% of our distribution packed into this portion here, and actually 25% of it is all over this tail. Similarly here we can see we've got a kind of this range here is much smaller than this, and similarly down here, okay? And we can say that. So we can say here, all three have positive, because the tail is kind of at the positive end of our number line, skew. All three have positive skew, and then I'm going to add an interpretation here. I know it only asked for 2, but in case this was the interpretation that you wrote, all three have positive skew. So all have more varied handspans above the median. Like so. Okay, lovely. 5 marks, brilliant. Okay, awesome. Moving on then. Pavel owns a music shop. He wants to investigate the keyboard sizes used by pianists with different handspans. He collects data about the handspans of the pianists who use his shop. The table gives information about the number of pianists with handspans in each of these 4 size categories. Pavel plans to sample 20 of these pianists by a stratified handspan size. So remember, stratified sampling is where our population is split up into clearly defined strata, into these groups, okay? And we want to sample proportionately. So if half of our population is children, then I need to make sure that half of my population of my sample is going to be children. So similarly here, we need to work out, okay, well, what's the total number of pianists that he's sampling from? And that total, if I add all of those up, is 160. And I can then work out, okay, well, what proportion of each stratum do I need to sample? So I can say, well, I need 20 out of 160. So I need 1/8 of each group. That's what I'm looking for, of each stratum. So I can work that out. I could say, okay, well, for A, okay, that would be that I need 24 divided by 8. That's 3. So I'm going to need to sample 3 from here. For B, we've got 65 divided by 8. Now, this isn't a nice number, but we can round that, okay? Actually, let's sample 8. For C, we can do the same thing. We've got 57 divided by 8 is 7.125. That is approximately 7. Okay, we'll sample 7 from there. And then we've got D. 14 divided by 8 is 1.75. So let's sample 2 from there, okay? So I'm sampling 3 from my group A, 8 from my group B, 7 from group C, and 2 from group D. And if I add all of those up, do I get 20? Yes, yes I do. Okay, I can do a quick check to make sure that I do end up with my sample size of 20. Now, quite a few people will leave it there, just think, oh, okay, I work out the proportions. But actually, it explains how he can obtain his sample. Well, this is the proportions that he's sampling, but how does he get there? Well, he now needs to do a simple random sample on each group. So he is going to number all the pianists in each group or stratum and use a random number generator to select the appropriate number of numbers from each stratum, selecting that or the respective pianists, like so. Okay, lovely. Question 2, 12 marks, nailed. Okay, moving on, we've got a cumulative frequency. So remember, the cumulative effect of something, the adding up effect of this. So we can see that between 170 and 180, we've got 16 people. Between 170 and 190, we've got 37 people, and so on. Remembering with a cumulative frequency diagram, we are plotting on the end points here. Okay, always plotting on the end points with something like this. Okay, so I am going to come across to 180. I am coming up to 16. Now again, we can spy here that vertically one of those is worth 2. So coming up, we get to 16, like so. 190, we're up to 37. 200, sorry, we're up to 55. 210, we are up to 74. 220, we are up to 83. And we just need to be careful here because this last one is not 230 as we might expect. It is in fact 280, but it's also not 100. So we have to be really careful that we spot that actually that point there is going like so. And then cumulative frequency begins with a C. We are connecting that up with a curve. like so. Okay, so I've connected that up with my curve, and we're now going to use this graph for our next part. So it says, the next part of the question, find an estimate for the number of the days where the snow depth was between 195 and 215. And when we do questions like this, we are always making sure that we are tracing across. So I'm coming from 195, 195, I am tracing up, and across, and I'm making sure that I explicitly write that value down because that's where you're getting your first mark. So here we've got 46, and then tracing across to our next value, 215. So 215 is in here. Okay, mine is in halfway along a square like so. Okay, and mine comes out at 79. Now yours might be slightly different to mine because your curve might be slightly different. That's fine. What's really important is that your answer comes from your numbers. So I then need to find the difference between those. I need to find how many people this gap represents. So we can do that by doing our 79 take away 46. Okay, I can go about doing that, and I'm going to end up with 33. Okay, now the mark scheme will give you anything between 31 and 37, provided that there is clear working from your graph, and we can clearly see how you've worked that answer out. Okay, lovely. Question 4, sorted. Question 6. Researchers investigated the effect of changing land usage on the amount of surface runoff water for areas of land around Brandywine Creek. They recorded the change in forest cover area, kilometres squared, from 1992 to 2000. They also recorded the change in the amount of surface runoff, millimetres of water, from 1922 to 2000. The table gives this information. So we've got lots of information. What's really important is that we look at what we're actually interested in. So here we're interested in surface runoff, and I'm already getting clues about what I'm going to have to do with this because we're told about change in surface area runoff rank. I'm probably going to need to do that, which makes me think we're going to need to do a Spearman's rank. Let's see. Ah yes, calculate Spearman's rank correlation coefficient for this data. So what we need to first and foremost do, right, the clue's in the name, we need to rank the surface runoff here. Okay, so I need to put these in order from smallest to largest. So I can go through and I can spot, okay, that's my smallest. Next up we've got that one there, then we're at 0. Okay, and we can then go in and we can fill these in. So we've then got our 5, we have got 6, going through 7, checking now, is this my smallest? Yes. 8, then up to here 9, then checking here 10. Have I got anything smaller? Yes, I have. 11, 12, 13, 14, and 15. And so we can put the ranks in, put them in order and rank them. And then this column asks me for change in surface area runoff rank, okay? Like so. And this is where kind of coming back to our formula sheet can be useful, because we can see here that actually Spearman's rank correlation coefficient, we've got this formula, and remembering that D is that difference, okay? So again, I'm thinking about what do I know how to do? Well, I can rank because it told me to rank it. It's now asking me to work out the change in the surface area runoff rank. And so I can go about working that out. And what is that? Well, it's these two numbers subtracted from each other. Now, strictly speaking, it does not matter which one you take away from the other. If you get the positive of what I get, that's absolutely fine. But 1 take away 15 gives me negative 14. because what we're actually going to do is we're going to square that. That's what our formula has in it. We're going to square it to make sure that any negative signs kind of disappear. So we can go ahead and we can fill that in. Like so. And what's really important here is that we are just taking that time to work these through. Like so, 11, 121, and then 0. And so we've got our d squared. Now coming back to my formula, we can see here we've got this capital sigma. Remember, that means sum. So we're going to need to add all of those up. And so I can add all of these values up. If I add all of those values up, I'm going to get 944. Okay. Once I've got that, we can now actually calculate this. So I'm a big fan of writing formulae down before I carry on. So here we're going to write that formula down. We're told that RS, okay, my Spearman's rank is 1 minus 6 lots of the sum of my differences squared divided by n times by n squared minus 1. And again, what's really important is that we make sure when we're doing questions like this that we identify all of those values. So n here is the number of pieces of data, and my number of pieces of data, we don't need to count them because we're told in the question there are 15 of them. So we can work this out. We get 1 minus 6 lots of 944 divided by 15 times by 15 squared minus 1. And when we work that out, we get negative 0.69. Now we are asked to interpret this in the context of the question. So firstly, it's negative. So that tells me it's negative correlation. Okay, we have negative correlation, and then we need to interpret that in context of the question. So reminding myself what my variables are. Okay, we've considered how surface runoff changes with respect to forest cover. So as surface as forest cover decreases, the amount of surface runoff increases. Like so. Okay, lovely. Moving on. Elizabeth wants to investigate possible drainage solutions that reduce surface runoff. She wants to establish whether a particular drainage solution reduces surface runoff. She plans to measure surface runoff in 10 areas for a year without the drainage solution. She will then install the drainage solution in 10 of these areas and measure the surface runoff for a year. Explain how Elizabeth's plan to collect data controls some extraneous variables. So extraneous variables, they are variables that are unrelated, okay? They're not related to what we're interested in, but they could interfere with the focus of our studies, okay? So we also need to include an example of an extraneous variable. So here it could be something like surface material. If you've got an area that's covered in tarmac, that's going to be very different to if it's covered in sand, if it's covered in moss. If it's covered in grass, all of these are very different. Kind of thinking about climate, if you're considering somewhere that's very hot versus somewhere that's quite cold, that could be very different, okay? So there are lots of different examples, but you could have different climates or surface materials. And then we need to explain how her plan kind of controls some of that. And so how does she do that? Well, some are tested with it and then tested without it. So areas are tested with and then without the drainage solutions. Okay. Elizabeth would like to reduce the time she is collecting data to 1 year overall. Describe how she could do this using a matched pairs approach. So what we do here is we identify areas that have the same profiles, such as rain or similar terrain, like so. Okay. Wonderful. Okay, awesome. Question 6, 9 marks achieved. Okay, moving on then. So Roxanne wants to investigate the resting heart rates of members of her running club. She believes that resting heart rates will be normally distributed. Here's her plan for investigation. So take a census of all of the members of the running club. Each one measures their resting heart rate, inputs it into a spreadsheet. Then she's going to construct a box plot to work out the mean, median and mode, and then work out the standard deviation. Okay, all great suggestions. And we're asked to discuss whether Roxanne's plan for collecting and presenting data are appropriate. Now, a quick look at the marks for this tells me it's 6 marks. And here, we're discussing whether Rox's plans for collecting and presenting data are appropriate. So here, we've got collecting and we've got presenting. So I'm thinking I need 3 points for collecting and 3 points for presenting here. And so kind of thinking about bullet points here to make sure you're giving all that information, really important. So I've said here, some runners might not fill in the spreadsheet. That could be a problem. Some might not fill it in accurately. Some people might not know how to fill something into a spreadsheet. Actually, the sample size is large, okay? In actual fact, it's a census, right? So you're sampling everybody in theory. So actually, that's really appropriate. Another potential issue is that runners might not accurately measure their heart rates. Actually, you could talk about Roxanne should measure them herself so she knows how they have been measured. When we then think about processing and presenting, actually a histogram might be a little bit better, because what that's going to allow me to see is that distribution of bell shape? Is that distribution a bell shape like a normal distribution would be? Mean and median allows her to calculate skew. Thinking about our formula sheet, we know that we need mean, median and standard deviation. Mean, median and mode need to be approximately equal, thereabouts equal, for it to be normally distributed, or approximately normally distributed. So absolutely, that's a great indicator that is correct. We then, coming back to data collection, actually does she need to indicate whether they're male or female within that? Now you could also talk about a box plot might allow you to see if the data is symmetrically distributed. You could talk about the fact that working out mean and standard deviation is appropriate for trying to work out whether it's normally distributed. But it really is thinking about what makes a normal distribution, and is this going to give me sufficient evidence? Okay, we need 3 points for data collection and 3 points for processing and presenting. On to our last little bit. So we've got researchers use the Peterson capture-recapture method to estimate the number of humpback whales off the coast of California, Oregon and Washington. They used aerial photographs to identify the whales according to the whales' unique markings. Now this is really significant because this is not our typical capture-recapture where we're tagging or marking fish, toads, whatever. actually we are using their markings that are already on there. So immediately I'm thinking, well, can they fall off? Not like they could if I was tagging animals. In 1995, they recorded the marking of 331 individual whales. In 1996, they identified 264 individual whales, of which 104 had been identified the previous year. So I always go about this with some fractions. So I know that the proportion that they recorded was 331 divided by the total number of whales that they had. And that then needs to equal 104 divided by 264. And I can then work out what my total number of whales is going to be by doing 104, not 104, sorry, by doing 331 times by 264 divided by my 104, okay, and we end up with 840 whales. Okay, now we do actually end up with 840.2, but we're going to round that to 840. Okay, we round down with something like this. Okay, discuss the validity and reliability of this estimate. Well, it's only valid, okay, 3 marks, so it's only valid if there are no births, deaths, migration. The markings can be seen clearly. Sampling method was the same each time. There's an appropriate time between samples, something like that. It's not valid if the markings cannot be seen clearly, if they've changed, if the population has changed due to births, deaths, migrations. Sampling methods might have been different, so essentially the opposite of when it is valid. And reliability is always the same statement, okay? Here, reliability is high because the sample sizes are large. If we had small sample sizes, then it would be unreliable, okay? Well done for completing this week's paper. Have a lovely rest of your day.